Let us do the analysis of AC through pure resistance. So in this circuit, we can see a resistance R is connected and it is being supplied through the alternating voltage, where the alternating voltage is defined as V equal to Vm sin omega t. This representation of the voltage is the time domain representation, where we can see that this lowercase v is indicating the instantaneous value and it is varying with respect to time. It's a function of time. Now, in the circuit, resistance is connected, so we can write the equation for the voltage drop as IR, and equation 1 and equation 2 can be written or equated as Vm sin omega t is equal to IR. So this gives us an equation for I equal to Vm by R sin omega t, where this term Vm by R is the maximum value of this current, and hence the instantaneous equation for the current can be written as Im sin omega t. This representation is a time domain representation. In order to write in the phasor domain, we can write this as I equal to Im angle 0. Similarly, for the voltage, we can write V equal to Vm angle phi. Phi is 0, so we can write V is equal to Vm angle 0. So maximum value of the current will be obtained when sin omega t is equal to 1. Equation 2, which is written in the time domain here, can be written in the frequency domain as the phasor domain as V equal to IR. The ratio of phasor voltage by phasor current is called the impedance of the circuit, and because the circuit is consisting of only resistance, so the impedance is equal to resistance. The unit of impedance is ohms, the unit of resistance is ohms. This is called the impedance of the circuit. Now, if we compare the equations 1 and 3, this is equation 1 for the voltage and equation 3 for the voltage, we can see that they are in phase and there is actually no phasor difference between the two. Now, as the voltage and current are in phase, so we can see in this diagram that we have drawn both the wave shapes for the current and voltage, and they are reaching their zero as well as maximum on either side at the same time. So we can say that both the quantities are in phase, that there is no phase difference between the two. Let us now calculate the power formula for the instantaneous power P. So instantaneous power P will be the product of instantaneous voltage and instantaneous current. So if we substitute the equations here, we get the formula for the instantaneous power as consisting of two terms, Vm by 2 and Vm by 2 cos 2 omega t. So if we look at the two terms, the power is consisting of one term, first term known as the constant term, and the second term is a fluctuating term, and it is actually fluctuating at double the frequency because it's 2 omega, it's double the frequency of voltage or current waves. Now, if we calculate the average power for the complete cycle, we need to integrate this from 0 to 2 pi. And after integration, we find that the power for the whole cycle will be equal to Vm by 2, which can be written in terms of the RMS values as Vm by root 2 into Im by root 2. So we can write the formula for the average power P is equal to VIRMS into IRMS, or we can write them as V capital I, where capital V and capital I notation is actually indicating the RMS values. The unit of this power is watts. So what we can infer here that for a purely resistive circuit, power is never zero, and we are getting the power P is equal to VI watts. So basically it's the resistance which is consuming power when an alternating voltage is supplied to it. AC through pure inductance. By purely inductive coil is meant that it has no ohmic resistance and hence no I square R losses. Basically, this is a coil of thick wire which has negligible resistance. Now, when alternating voltage is given to this inductive coil, a back EMF is produced due to the self-inductance of this coil. This back EMF will oppose the rise and the fall of current through the coil. So there is no ohmic voltage drop, so the applied voltage has to overcome this self-induced EMF. That is the applied voltage denoted by the lowercase v is equal to Vm sin omega t, where this is the instantaneous value of the applied voltage. So this we can write that V is equal to L di by dt. Now V equal to L di by dt. This is written in the time domain. If you want to write this in the frequency domain, then we'll have to write this capital V as j omega Li, where d by dt can be written as j omega. So in this time domain, we can now write this equation as Vm sin omega t. V is equal to L di by dt is equal to Vm sin omega t. Now, from this equation, we can write di is equal to Vm by L sin omega t dt. Integrating on both the sides, we can write the expression for I is equal to minus Vm by omega L cos omega t, which can be written in terms of sine as sin omega t minus pi by 2. Here, Vm by omega L, this term omega L is represented by a variable known as XL. This XL is known as the inductive reactance. Inductive reactance of the coil is XL, which is equal to omega L, where omega is 2 pi f. This entire term Vm by XL is equal to Im, that is the maximum value of this current. So, what do we get here? If we look at the equation 5, we get the equation for current as Im sine omega t minus pi by 2. And if we compare the equation 1 with the equation 5, we can see that there is a phase difference between the voltage and current. And the current is lagging behind the voltage by pi by 2 or by 90 degrees. So if we plot the curves of these two wave shapes, that is the current and the voltage wave shapes, we have to create a phase difference of pi by 2. That is, the current wave shape is actually starting after pi by 2 radians. That is, its 0 will start after pi by 2 radians. Now from equation 3, this is our equation 3. From this equation, if we take the ratio of phasor voltage by phasor current, that gives us the quantity known as the impedance. Now for this circuit, which is consisting of only the inductance, we can see that the impedance is equal to XL, but we'll write it as JXL, that is J omega L. That is, we have seen here that this XL is written as JXL, that is J omega L. Now we'll write XL is omega L, that is 2 pi FL. The unit of XL is in ohms. So we can write this as 2 pi FL. So we can see that the inductive reactance depends directly on the frequency F, and higher the value of the frequency, greater will be the reactance offered. Also, if we look at the expression for V and I, which we have deduced, the expression for the voltage V equal to Vm sin omega t can be written in the phasor form as V equal to Vm angle 0, and similarly I is equal to Im sin omega t minus pi by 2 can be written in the phasor form as Im, I equal to Im, and angle will be pi by 2, that is 90 degree. So we'll write here minus 90 degrees. This minus sign also indicates that this current is lagging behind the voltage by 90 degree. Okay, let us now see how to calculate the instantaneous power for this circuit. So instantaneous power is given as, we'll be writing this in the lower case P equal to instantaneous voltage multiplied by instantaneous current. So we are writing the equation for both, and we derive this value for the instantaneous power, that is minus Vm Im by 2 sine 2 omega t. In order to find the average power for the circuit, we'll be integrating from 0 to 2 pi for the complete cycle. So we find that when we integrate this comes out to be 0. Graphically also we can plot the power. So we can see here that we are getting the alternate positive and negative half cycles for the power. So the average power will be 0. Or in other words, we can say that the average demand of power from the supply for a complete cycle is 0. That is, when the circuit is having the inductance only, then the average demand of the power will be 0. If we wish to represent the vectors V and I, then we can make them like this. As this is our voltage V and this is our current I. The current is lagging behind the voltage by 90 degree, and the anticlockwise rotation of these phasors is considered positive, which are rotating at omega radians per second. Now in this graph, if we see the maximum power, the maximum value of the instantaneous power is Vm Im by 2. So that is indicated here, Vm Im by 2. That is the maximum value of instantaneous power. AC through pure capacitance. When an alternating voltage is applied to the plates of a capacitor, the capacitor is first charged in one direction and then in the opposite direction. So here the supply voltage is defined as instantaneous voltage V is equal to Vm sine omega t. Let V is the voltage which is developed across the plates of the capacitor at any instant. Q is the charge on the plates of the capacitor. So we can write Q is equal to CV. In place of V, we can write Vm sine omega t. Now the current is given as the rate of flow of charge. So we can write I is dq by dt. That gives us equation 2. Differentiating this, we have Vm upon 1 by omega c cos omega t. Now here Vm upon 1 upon omega c. This is called the maximum value of this current, which will be obtained for when sine omega t plus pi by 2 is equal to 1. This quantity 1 upon omega c is also known as xc. So this is another variable, that is xc. This xc is known as the capacitive reactance and the unit is ohms. Now if we compare this equation of the current with the equation of the voltage, then we can clearly see that the current is leading the voltage by pi by 2 because of this plus sign. So because of this plus sign, we can see that the current will lead the voltage for a purely capacitive circuit. Let us see these graphically. So graphically we can plot V and I, the instantaneous values of the voltage and current, so that the variation can be shown with respect to time using these equations. Now we can see that the maximum value of the current is obtained first and then the maximum value of the voltage will be obtained. So there is a difference of pi by 2 between the two quantities, voltage and current, with current leading by voltage by 90 degrees. Let us calculate the instantaneous power in this case. Okay, so before going to instantaneous power, let us see Xc, that is the also known as capacitive reactance, which is 1 upon omega c. In place of omega, you can write 2 pi f, right? So that is 1 upon 2 pi f c. Okay, and let us see now instantaneous power. So if you look at the instantaneous power, this is the product of V into I, that is Vm sine omega t into Im sine omega t plus 90. So that gives us Vm Im by 2 sine twice omega t. So we can say that the power is having the frequency double that of the applied voltage or current. And if we calculate power for whole cycle, capital P is integrating from 0 to 2 pi for the complete cycle. So this comes out to be 0. So we can say that for a purely capacitive circuit, the average demand of the power from the supply is 0. Similar the case when we obtain for a purely inductive circuit. Now from the equation 2, we can also write the current as C dV by dt for the time domain. And if you want to represent this in the frequency domain, then d by dt will be replaced by j omega. So we have I equal to c j omega v. The ratio v by I is known as the impedance Z of the circuit, and which is equal to Xc here, and Xc is 1 upon j omega c. Okay, so this is Xc. This complete is Xc, that is the capacitive reactance. So for this circuit, the unit is ohms. For this circuit, the impedance is Xc, that is 1 upon j omega c. Now for a DC, we know that omega is 0, that is F. We are writing F is 0, so omega is 0, which is 2 pi F. So let us see what impedance will be offered for a purely inductive circuit. So for purely inductive circuit, XL, which is denoted as ZL, is equal to 0. This is XL, so it's a 0. So that indicates that the inductor will act as a short circuit. If we see for a purely capacitive circuit, ZC, which is our XC, so XC is 1 upon 2 pi FC or 1 upon omega C. So if I write omega equal to 0, I'll be getting Xc equal to infinite. That is the impedance that is offered for a purely capacitive circuit is infinite to DC supply. So the capacitor will act as an open circuit when DC is applied to it. Now let us see the summary of all the elements that we have seen so far: R, L, and C, all the three passive elements, expression for impedance and expression for admittance. Impedance is for a purely resistive circuit, Z is equal to R. For a purely inductive circuit, Z is equal to J omega L, that is JXL. For a purely capacitive circuit, Z is equal to 1 upon J omega C, which can also be written as minus JXC. When J we are writing in the numerator, it will be minus J, minus JXC. Now the reciprocal of the impedance is called admittance and denoted by capital Y. So admittance is 1 upon Z, that is the ratio of current by voltage, right? And we will be expressing this as G plus JB, where we are representing admittance as Z as R plus minus JX, where this X may be capacitive or inductive. It is of two types. It may be capacitive or inductive. So that we'll see in the next discussion when we are taking the combination of the resistance and inductances, or resistances and capacitances. So admittance is reciprocal of impedance, and for a purely resistive circuit, admittance will be written as 1 by R. For purely inductive, it will be written as 1 upon j omega L. For capacitance, it will be written as j omega C. So this is how the Y will be written. The unit of Z in all the three cases, the unit of Z is ohms. The unit of Y is ohm minus 1, you can say ohm inverse, or you can say mho. This is also known as mho, or another name of this unit is Siemens.